Okay, so I feel like talking a little bit about this idea of Galois descent. And so there's actually a decent little kind of review paper, sort of expository type paper by a guy named Reuter called Galois descent that explains it pretty
Boy, as we're adapting to this new
simply.
interactive whiteboard format, I'm realizing that I'm already, all right, so that means I have to either use my paper notebook to take notes, or else just let your whiteboard be my notes. Okay, go ahead.
Yeah, I can easily email you this stuff if you want.
Okay.
So that's like one thing that's one source of information on it. I actually got it.
Written? Do you know when this is written?
Pretty recently.
Okay.
So then there's this other thing. It's where I first started learning this stuff.
Yeah.
Which is a book. So it's called, The People. Sorry, I have so many windows up on my little screen. I have to like keep bouncing back and forth between Galois and something like Shamuali. Sorry, I can't pronounce that name.
Okay.
Shamuali. That's a Z.
Okay.
And that book I got to reading it when I was trying to understand this Albert Brouwer-Hasse-Noether theory.
Yes.
Like completely mysterious to me at the time. And so their book is just about that.
Did you say theory or theorem?
Theorem is what I should have said. Okay. But it's not like all theory of this stuff.
Well, I might as well write down those 4 people's names. Albert. These sound like classical names.
Yeah, Albert Brouwer, Hasse, and Noether. And
now there's something funny about that, right? Because Noether was Brouwer's teacher or something. They're putting the teacher's name last.
Well, I was just doing them in alphabetical order.
Oh, okay. Maybe I should figure that. Albert's an American, right?
Yeah, so he sort of was a little bit separate.
Okay.
From the rest of the gang in his contributions.
Okay.
It's an interesting story. Yeah. So this book here is all about that. So I guess like at the time when I was first trying to understand this, I was like completely mystified by what Galois theory, which I sort of knew was like about fields, would have to do with classifying central simple algebras, which I knew were like things that give rise to the Brouwer group. That is the Brouwer group is a set of Morita equivalence classes of those things. And I was thinking like, how in the hell does Galois theory apply to that? And so I eventually figured it out. And if I'd read this thing by Reuter, it may have happened faster. But anyway, so what's the idea? So none of them explain it quite nicely enough. So I'm going to try. But so the idea is Galois descent is a very general concept. And so the idea is that you have like some extension of fields. So you have like a little field F included in a big field F prime. Probably I want it to be like a Galois extension, just to be careful. That's all I care about.
So they're going to have Galois descent along this inclusion
along this thing, yeah.
Along this possibly Galois inclusion,
yeah,
of fields. Well, the big question is, which end is up, right?
Well, we're going to get to it. So,
Okay.
so I just want to, so then the Galois group is going to be running around all over the place. So this is like the Galois group of F prime over F, or whatever they call it. So I'll just call it G. And so the type of question that you're going to ask in this Galois descent game is, you have some kind of algebraic gadget, like, let me just like say like an associative algebra, for example, but really any sort of algebraic gadget, well, some large class of algebraic gadgets that could be defined over any field. And so we want these algebraic gadgets to have the property that when you have one over F, you have such a gadget over F, you can get from it a gadget over F prime. So there's like, I could call like, get like, say C of F is like some category instead of saying algebraic gadget all the time, I'm going to sort of like pick an example. So I'll just say like algebra, category of algebras.
Okay.
Over F, but it could be like for example, it could be an associative algebra or a Lie algebra or a Hopf algebra.
Yeah.
And so then similarly, C of F prime is the same kind of thing for F prime. And then what we want, and indeed have in those examples, is that we have this, sorry, sorry, I think I won't draw things you're saying like which way is up, but I don't want to write, I'm confused by that right now. So what we have, I will draw horizontally therefore.
Sure.
So we have, let's see, we have a map I'm positing that we have a map from category of algebras over F to the category of algebras over F prime. And typically the way it works in this game, by the way, is that like if you have some algebra over F, it's going to be like a vector. I mean, there are more general examples. It could be like a variety. It could be all sorts of stuff. But let's just say like it's a vector space over F equipped with some algebraic structure. So then typically the way that this map would work, by the way, is that you take your algebra, which is a vector space over F, and then you tensor it over with F prime, and you get So that's sort of like the kind of example that I would have in mind. That's how this would work. Okay. And so then the question is, the big question, well, I'll state the question in a crude way and then like in a better way. So the crude way is like, that you might ask is like, when does an algebra over F prime come from 1 over F by means of this functor here? That's like a very
I'm dying to ask, does that mean, is that when does it descend or when does it ascend, or you don't
that is called descent.
Okay.
So I don't.
So
that's why I'm getting confused actually, because the way I think of it, like categorically, I think of it as something that like there's sort of like a forgetful functor going from C of F to the C of F prime.
Yeah, it seems like we're putting the focus on the upstream thing, but again, we often do that. We often talk about categorification, or people think more categorification than decategorification. They think more about quantization than about dequantization.
Right. Yeah. So we're. I mean, so this
Because it takes some effort, you have to put some work into going the wrong way.
Right. So I mean, this natural way we like consider
Falling off a log.
But yeah. So we don't want to write a whole book about that. How to fall off a log. Yeah, I mean, you can't really do it, but like the idea is you like want to know like when you can go up and how many ways can you go up and things like that. And unfortunately, I guess that is called descent.
Well, it's going to work out either way. I mean, because you always have the choice to think algebraically or to think geometrically, and just which one is.
So there is a geometrical outlook that makes this name descent much more reasonable. But I'm not going to try to bring in that geometry at all. In fact, I'm just going to try to think about the.
But I think that's right. But maybe right. So maybe that is one of the magic words, though. Descend. I want to say something like descent with respect to a covering or something like that.
Yeah, exactly. So so
covering is going down.
That's right. So the idea is that like so I mean, okay, you're pushing me into this. It's gonna take more than 15 minutes at this rate, by the way.
I'm sorry.
But we have got this inclusion of fields, but you sort of want to think of it geometrically going the other way as some kind of geometrical map going backwards, and then you might have some space associated to f prime or something like that, and we might want to know like when does a bundle over that space descend to a bundle over the base space,
which really does sound like in order to do that it might require some gluing in order to get to descend.
Right. So we're not, and so there are approaches to this stuff that become very geometrical and think about things like sheaves and gluing and so on. But I'm going to give sort of approach I will talk about is related, but it's not going to be. I'm not going to be harping on the geometry at all. So,
sure. Okay. But I just want to throw in one more thing, which was I've told you this before that when I was learning a bunch of things for the first time, I spent so much time trying to remember what the difference was between a cover and a covering. And later I found out that it's really much more important that they're the same thing than that they're different things.
So one slightly more refined way to describe the basic question is like something like this. So like describe. Well, maybe we're not going to get quite this far. Describe. Well, okay, this is like a bold way to put it. Describe the category of algebras over F in terms of algebras over F prime, and also this Galois group, which acts on things and its actions. Its actions on various things.
I do have another stupid question coming up, but I'll wait. Go ahead.
So I think, I'm going to actually like answer a watered down version of this question. So I'm not going to try to describe the whole category. So what I'll do is I'll say like, so describe isomorphism classes. I start writing iso classes. So describe isomorphism classes of objects in C of F, algebras over F, in terms of C of F prime and G. Probably this is all very groupoid theoretic. So when I talk about the categories of these algebras, I should probably might as well really be saying the groupoid of them, in fact, because we're never going to do anything involving non.
Well, that's an interesting question, but you might be right. I mean,
in my presentation, I'm not trying to speak authoritatively on this. I'm just talking about like what I'm going to do.
Sure.
So you might as well think of these categories as groupoids for what I'm going to do, which makes things, of course, easier. So, okay, so here's the answer. I bet we could probably, anyway, I'm not going to try to keep making things better. I'm just going to try to get some idea across. So, so instead of saying objects of C of S, I'll call like an algebra over F. So an algebra over F is the same as what I'll call a weak fixed point of the action of our Galois group.
Yeah, this is really leading into my stupid question. Keep going, keep going.
Okay, action of our Galois group on, so this Galois group acts on everything associated to the field F prime. It acts on the field F prime. And you can take an algebra over F prime and get a new algebra over F prime by applying an element of the Galois group. So the Galois group actually acts strictly on the category of algebras over F prime. So they're and so this is like the short way to say the answer. If you're happy,
also in some sense the good way, but go ahead.
Yeah, right, exactly. So okay, so if you're happy with that, that is, if you're happy with that, then from then on, the stuff that they make a big to do of is to like
methods of calculating that.
Yeah, sort of
with gauge fixing, a lot of gauge fixing, something
like that. So what I'll do is I'll sort of say what I mean by weak fixed point, which you sort of already know, and then we'll see how it's connected to the cohomology of this Galois.
Yeah,
that's sort of the goal here. So what's a weak fixed point? So the idea is so this may be already sort of strictifying things a little bit, but not in any bad way, I guess. So we'll take so what it's going to be is it's going to be one of these algebras over F prime. So then so I'm saying that you can act by the Galois group and get a new algebra over F prime, which I'll just call G of A. So that's like an algebra on a new vector space, which is obtained from the original vector space by using the Galois group. So what we want is for each of these group elements, we want an isomorphism, we call it like alpha of G, from this new algebra to the algebra A. So these are isomorphisms. But then we want these isomorphisms to be coherent, to be nice. And so the important one, the important thing is that
I'm saying yes, because I always get this part of it wrong. I always get confused about what the proper coherence conditions are, but go ahead.
Yeah. So the main thing is that concerns the fact that you can act on A by a product of group elements.
Yes.
And then, well, a product of group elements is a group element. So there will be an isomorphism from GH of A to A.
Mm-hmm.
But GH of A, I'm assuming that's equal to G of H of A. I'm assuming, to keep things simple, and it happens pretty naturally, that we have a strict action of the group on this category. So GH of A is just equal to G of H of A. So we can like let the G just sort of hang out in front, and then there'll be an isomorphism from H of A to A. And so we get the functor G applied to alpha of H. So alpha of H goes from H of A to A. And then and G is the action by G is a functor, so we can tack a G in front of everything there. So we get that. And then GA is isomorphic to A. And so that's that isomorphism is called alpha of G. So we want these guys to commute. So let me just write that down in more equation-y language. So it says alpha of GH is equal to, I guess I'm going to write composition in the backwardsy way that it's more traditional. So G of alpha of H. So that's the law that we want for the action to be coherent. There's also some stuff about the identity. So this is like
yes.
Law.
And again, when I say yes, I mean that's the kind of thing I always get confused about. How much do I have to worry about that, et cetera, et cetera. Yeah. Go ahead. Yes.
Yeah. I will temporarily not worry about that. So what I'm going to show you is that this equation here.
Yeah.
Once we get ourselves, once we do some stuff, this is going to be a cocycle condition.
Sure. I mean, it almost already looks like a cocycle.
But, well, it is a cocycle condition. Yeah. But anyway, I'm gonna lay it all out, and then then some other, like there's some other law you might want, right? Because you could act by the identity.
Yeah. And
so there's some kind of thing you should be concerned about.
Yeah.
This thing. And the most obvious law, well, anyway, there's something you could worry about here. And so that winds up being connected to what we call normalized cocycles if we
right. And I get confused about, to what extent that normalizedness is optional, and if it is optional, how can it be optional? It seems confusing, but okay, but go ahead. Yes.
Yeah. So, but let me focus on this first one.
Okay.
So now, okay. So notice all these three algebras here, they're just isomorphic. But what people do, wittingly or not, is they take this category of algebras over F prime.
Yes.
And they replace it with a skeleton of that category. So an equivalent category where isomorphic objects are equal. So
certainly that's something you can do. Are you saying you always do this in a certain version of this game or something like that?
I think implicitly they always do this.
Okay.
Most of the people who do this stuff never talk about groups acting in categories or anything.
Right.
So they do so much. They do things so terribly that it's sort of an exercise to translate what they're doing into some cleaner language, and then you have to say oh, they must be taking a skeleton. That's sort of my
sure.
So okay, so now in other words, I will take all these different isomorphic algebras to be equal.
I mean, sorry, I was just taking skeleton. I'm not even sure I noticed the metaphor fits together, but that's also sometimes called, cutting out the flab, which kind of makes sense. If you cut out the flab, all that's left is the skeleton. Okay.
Yeah, that's right. So then in that situation, in the skeleton, all these guys are just, we might as well just say they're all A, they're all equal to A. And then all these isomorphisms are just called automorphisms of A. And so then, okay, so in a skeleton, so then things, yeah, so all these isomorphisms are, or can be taken to be, are elements of aught A, the automorphism group of A. So we think of these, so we think of them that way. Sorry, no, this is where the kind of place where I hate having finite sized pages, but I'll.
Okay.
So what we've got here is this. Sorry, what we've got here is this map that I've been calling alpha. And so it's assigning to each element of our group. Now we're just thinking of it as an automorphism of A. So that's how we think about it in this skeleton way.
Yeah.
And then, well, the equation that it has to obey this equation. The equation looks just the same, but maybe when you're multiplying things in an automorphism group, you don't necessarily write compose. Oh, you can do whatever you want. Yeah. But anyway, the main thing is I want to get this equation here again. I'll still write alpha of G. See that what I said? Yeah. Okay. So yeah, so that's what we've got. And I guess the main upshot is just this, that so in fact, this says that this equation here just says that alpha is a one cocycle on the group G with coefficients are valued in, I guess you say, valued in the group aught A. Now, one interesting little thing here that's nice. So normally we think about cocycles on a group. Traditionally, we think about cocycles in a group taking values in an abelian group. But as you know very well,
there's different traditions, but yes, go ahead. Yes, that's right. Go ahead.
Yeah. So, but there's this nice thing that for zero cocycles, they can take values in any set, and then for one cocycles, well, here we're multiplying, so a set wouldn't be good enough, but we can develop the theory for one cocycles taking values in any group, not necessarily abelian. So this aught A is typically a non-abelian group, but that's okay. So that's nice. So let me just sort of remind ourselves, just as I kind of check, and it's possible that sorry, I'm messing around here. It's possible that some little glitches in convention will show up at this point, but so
right.
For example, like the order in which I wrote the multiplication, I may have picked the wrong convention or something, but
Sure.
So let me just sort of remind myself like what the boundary or co-boundary of a one chain is. So a co-boundary of a one chain, like D alpha, is a thing that's going to take two group elements for as arguments, because it's a two co-cycle. A two, it is a two co-cycle, but it's a two co-chain. And the way I always remember this is that the way I remember it is you've got a bus. Alpha is like a bus that holds one person, and you're trying to stick two kids on the bus, and there are various options for doing it. This is a stupid story. and
no, okay, go ahead.
Yeah. And so
I'm trying to see if I recognize this stupid story, but go ahead. Yes.
So, well, sort of slightly degenerate case of this stupid story. So, because it's a very small bus, because it's just a one, we're just taking D of a one cochain. So the story is not as fun as usual, but anyway, one possibility is you let one kid sit out in front of the bus, on the front of the bus. Sorry. My computer is starting to slow down. I'm gonna turn off the video of me.
Okay.
So that one can hop out in front of the bus, or you can bunch.
This sounds very dangerous, and
that's very dangerous. Well, or you can bunch two kids up in one of the seats. Here, there's only one seat. And speaking of dangerous, the other last option is you can just throw the very last kid off the bus. So H is just gone there. So that's how this works. And well, this is maybe just for fun. Like if we did it one notch, if we did boundary of a two co-cycle, it would go like this. You could have the G could be in front of the bus. You could pack the kids G and H together, or then you could pack the kids H and K together. So it keeps on going like that. And then
this sounds like some sort of pigeonhole principle.
Yeah, it's something like that. And then, but then the weird option is that then the last guy just falls off. So that's the kind of thing. But we're in a very degenerate case of that. Of that story.
Yeah.
So okay, so this is what the co-boundary of a one cochain is. But so then a co-cycle would be when that's zero. I'm writing things additively now.
Okay. Which is supposed to mean that they probably are abelian, or?
That's almost hint. Yeah. Well, that's like. Well, yeah. That's notation that's good for abelian. This would make sense in the non-abelian case. But an alternating product.
It might.
We're going to switch to the non-abelian case in just a second here. Yeah.
Okay.
So this is still written out in. Yeah. Oh boy. Yeah. So still written out. Yeah. Still written out in additive notation. This is equal to 0. Oh boy. Now, let's see if I'm going to manage to correctly. Let's be bold and try to do this in the non-abelian case.
Okay.
And then what we're trying to see that if we get the if we get this formula here that we have.
Okay.
So let me just give it a shot. I think I will.
Okay. And I'm not very responsible for catching your errors, because I'm halfway following this, and if I would really slow us down if I really try to catch all the errors. So go ahead. Yeah.
So it's well, okay. I hadn't really planned to do this, but okay. Right. So the idea is that before we had in this sort of nice form where we expressed alpha of GH in terms of two other things. It's actually like a convenient way to think about it. Here, alpha of GH is sort of like in the middle of some expression. So yeah, so if I write it multiplicatively, that minus sign is an inverse. And so that these guys multiply to 1. Yeah, here I'll just do it. So we can solve for alpha of GH. So we left multiply by the, I didn't want to get into such a technical junk, but anyway. Almost there. So I can left multiply by the inverse of this. I can right multiply by the inverse of this. Now everything has these annoying inverses, so I'll just take the inverse of everything. And then I guess things flip around here. You get alpha of G, alpha of H. And so that's what I'm getting.
Okay.
And now let's compare it to what I had written. And I think it was a little different.
But I saw places where there could have been room for
right.
little.
Yeah. So the only difference is here I'm writing multiplication in one order.
Yeah.
And here I'm writing, back then I was writing it in the other order. That's the only difference. That is,
it's gonna work out somehow.
In A. So for example, if I had been really organized, I would have not used the stupid convention of composition. Just use the left to right formula for composition.
Right.
And then it would have worked out exactly on the nose, sort of by accident.
Somehow it's going to work out the correct way.
Yeah. But anyway, no, I'm telling you, yeah, you're being, you're not believing me. But I'm saying that, like, if I had not written composition in this stupid order that everyone uses that you don't like,
I could halfway believe that, but I I'll have to go home and check for myself.
Yeah. Then in fact we would get exactly the traditional convention. I mean, to the extent that there is even a traditional convention for the
right
co-boundary formula in the non-abelian case.
Right.
But anyway, so that's the point. So, and then I guess you can go further even, and you can. So we've seen that you get, I mean, so far what we've seen is that, like, algebras over F. Sorry, we've seen that weak fixed points are giving us these cocycles.
Yeah.
And the cocycles are giving us these fixed points. But then to go further, you'd like to say that, like, there's actually a groupoid of these weak fixed points. So you can prove them isomorphic. And so you would show that weak fixed points are isomorphic if those cocycles differ, if and only if those cocycles differ by a co-boundary. So that's another type of calculation of this sort.
And does that tend to, shift your cohomology index by 1 or something like that when you do that?
Yeah. So in
some sense. So yeah.
So then you're considering when one cochains differ by a 0 cochain. So there are basically two ways to make this fairly pretty. So one is you say something like this. This is like the lowbrow way to say it. You say, like, isomorphism classes of algebras over our little field are in bijection to isomorphism classes, sorry, F algebras over F. Isomorphism, sorry, that's not what I wanted to say. Well, sorry, let me just get it to the whole. So I mean, there's sort of a bunch of things you can say, but sorry. Let me just go straight to the punchline. So isomorphism classes of F algebras correspond to the first cohomology group of G with coefficients in odd A.
Yeah.
So that's working with things with sets of isomorphism classes. But then there's this more highbrow way where you say, hey, don't take the cohomology group. There's actually a groupoid running around, where the objects are one cocycles and the morphisms, the isomorphisms, come from the zero cochains. So a zero cochain can take you from one D of a zero cochain can take you from one cochain to another. So you treat the first cohomology not as a set basically, but as a groupoid. And then so then you say that the groupoid of F algebras is captured by that groupoid defined using cohomology. So that's like the more royal way to polish it all up.
Yeah.
But this is sort of nice in some ways because people have all sorts of tricks for calculating these cohomology groups.
Right.
Go ahead and do that. So a large part of that book that I mentioned,
Yes,
it is about like how you actually calculate these kind of cohomology groups.
yes.
So then I guess the Albert Brouwer-Noether-Hasse result, one of the results was like trying to classify, like for example, figure out the Brouwer group of the rational numbers was one for their big.
Sure.
And so they did that using this method by classifying the central simple algebras over the rationals using lots of Galois groups. So anyway, but the basic idea anyway is, as you see, really nice and simple, and then that sort of sets the stage for doing all these kind of calculations. So that's it. I took
Okay. Okay. Well, so there's a lot of things I have to think about there. I mean, partially it's that, so much of it seems familiar, but I have to think about the language and all stuff like that. There's a whole bunch of things I have to think about. Even if it ends up being very familiar, and if it doesn't end up being very familiar, I still have to think a lot about it. But I have one particular, my stupid question that I've been saving up to ask you now is where did this screen come from? Is this an earlier screen?
All right, let me just say I made a mistake.
Go ahead.
So here, these are isomorphism classes of F algebras.
Yes.
But not all of them, because we're picking one particular F prime algebra A and working with that. So these are the F algebras such that that when you turn them into F prime algebras, they give you that one.
Yes. They may be some sort of homotopy fiber or something like that. But go ahead, yeah.
So that's so basically what we did is we took a groupoid problem and we sort of turned it into a group theory problem by sort of working one object at a time. And so we get and then I forgot. So yeah, so you have to, yep, okay. Anyway, go ahead.
So the question that I've been saving up for the past some minutes is I'm trying to decide to what extent. So you have this thing that you were calling C, which is some sort of higher functor, like maybe a 2 functor, or it's some sort of higher functor. Well, I mean, you might not have emphasized the fact that it's a higher functor, but really it is, and it looks like you have it being algebraically covariant. If I didn't get things screwed up.
Yep.
And but being a higher functor, I'm tempted to ask questions about it, like about. And I'm very much in danger. If I try to get it right, I'm very much in danger of getting certain things backwards here about whether I should be thinking about homotopy colimits or homotopy limits or whatever like that. But I want to think about preservation properties that C has as a higher functor, preservation of homotopy limits and or homotopy colimits, and particular preservation of homotopy invariance or homotopy co-invariance or something like that. And I'm wondering if you're telling me that what we're doing here, and again, there's many variations on this question, but one naive version of the question is, are you telling me that there are certain situations where we automatically or semi-automatically are going to know that C does preserve some special homotopy limits or some special homotopy colimits, or maybe even all homotopy colimits or all homotopy limits or something like that? And again, whether it's homotopy limits or homotopy colimits might end up depending on whether you're looking algebraically versus geometrically or something like that. But that's sort of my stupid question. Yeah. I mean, is some sort of preservation of homotopy limits or colimits, is that part of the axiomatics of this setup, or is it, or do we get things to work even when that doesn't happen, or I don't know.
I think this answer here holds for a really huge class of things that you could call algebras over F.
But that still could be.
Yeah, I think this answer here is like a theorem saying that this C does preserve certain.
It looks like some kind of homotopy invariance, the way you have it set up, because fixed points, that's like the invariance of a group action, and that's a kind of limit. Yeah,
so F is,
and we're doing it weak, so it's homotopy limit.
Right. Yeah. So F is the G invariance in F prime.
Yeah.
And then we're saying that C of F is the homotopy G invariance in C of F prime. So it seems to working.
Yeah. So I like I say, I'm not sure of the generality of all of this. It might be that we're not dealing with a very general preservation of limits. It might be just preserving some very special homotopy limits or something like that. But anyway, this is an issue that I wanted to raise, the issue of taking that kind of viewpoint, of trying to figure out what kind of homotopy limits are being preserved by some sort of higher functors here.
Yeah, that's really nice. Also, you're making me want to think about to what extent we needed fields here.
Right.
I guess why you made me think about that is because if you're trying to preserve limits or colimits or something, the category of fields is pretty, pardon the pun, pretty limited when it comes to what kinds of things you can do.
But that could still be useful even sometimes. But yeah, those all sorts of possibilities there. Yeah, and the way you did seem sort of indifferent between groupoids and categories. I guess that's also a clue to what's going on. That, what am I trying to say? That the maybe forgetful functor from categories to groupoids, maybe that tends to preserve homotopy limits, if I didn't get it backwards. I don't know. Again, these are things I'd have to think about.
Yeah, I don't.
And these it could easily be that these are things we're already supposed to know, but again, maybe not. But these are things to think about.
Mm-hmm. Yep.
So yeah, so when I start talking, which I think before I start talking, I think we're gonna try and turn the camera off just so I can get some stuff sort of halfway ready.
Yep.
But when I do start talking, it certainly would be interesting to try to figure out the connection between what you've just been talking about here and stuff that I'm going to be talking about. I mean, it might be that it's exactly the same thing, or it might be that there's just relationships of some kind. When I start talking about it, it still seems to me like the way I'm going to be talking about it is, in some sense, going to be more of a Tanakian viewpoint. But I'm not even sure if it is more of a Tanakian viewpoint. It could be that they're both actually equally Tanakian. I don't know. But anyway, let's maybe try turning off the camera while I
Sure.
Yep. Try to figure out where I left some stuff.
Yep. Do that if I can. Okay.
Okay, so this is really a follow-up to what I've been talking about the last couple of weeks. And once again, I'm claiming that there's some nice progress here in terms of what I think I understand. And this progress takes the form of, the sort of fruition of a sort of plan that we had. So, I mean, what was this plan? What was the problem? What was the plan for how to attack the problem? Well, I mean, I'm trying to remind myself of what the whole situation is. So, I mean, in one way, the big plan is I'm trying to understand something that might be called arithmetic geometry. And but the way I'm approaching it is I'm trying to understand a lot of classical number theory stuff, like reciprocity laws and things like that. For example, cubic reciprocity and Artin reciprocity and things like that. That's one of the things I'm really trying to understand, but I'm trying to understand it from a certain kind of geometric viewpoint, which I think might fit into what people would refer to as arithmetic geometry in a certain way. But as usual, I'm trying to reinvent it myself and taking somewhat of an eccentric viewpoint. So we'll see how that goes. So I've got this idea that I really want to understand the idea of a torsor over a number field. And in particular, a G torsor, or maybe I should call it, I'll call it a G torsor over some number field. But G should be, for the moment, G should be a finite abelian group. But you should really anticipate, that we're going to generalize that eventually at some point. I mean, two obvious ways that we're going to generalize it are we're going to eventually be really interested, hopefully, in G torsors where G is a non-abelian group. G torsors over a number field where G is a non-abelian group. And also, instead of just having G be a finite group, we're at least going to have G be a profinite group. And somehow, right, the mechanism of how you think about profinite groups versus the way how you think about finite groups, there's ways sometimes that you can sort of you sort of have an optional way of thinking. I mean, right? In some sense, when you're trying to understand the profinite stuff, there's ways you can get away with pretending that it's really just finite. Because in some sense, profinite things are a certain kind of limiting case of finite things. So, you know, I'll probably talk as though we're dealing with finite things here, but at some point it may be important to really think semi-seriously about things that are profinite, groups that are profinite and stuff like that. So yeah, so we're really interested in this idea of G torsors over a number field, where G is a finite abelian group, and we have two important examples so far, and we're really trying to pretend that those two important examples are like a really big part of the subject. Like, so one example is G is Z mod 2, and another example is G is Z mod 3. And one of the distinctive things about Z mod 2, that group, Z mod 2, that finite abelian group, it splits over the rationals. Already over the rationals, it splits. Whereas Z mod 3 doesn't split over the rationals. It doesn't split until you get to the Eisenstein rationals, the field, this Eisenstein field, the field of Eisenstein rationals. And so that's a nice contrast in terms of the examples. And, you know, and then somewhat ambitiously, I was sort of saying, well, as soon as we can understand that one example of Z mod 3 and, you know, how it's more interesting, how it's more complicated than the case of Z mod 2, due to the fact that it doesn't split over the rationals, then I was somewhat ambitiously saying, well, that's going to let us understand the completely arbitrary case as soon as we do Z mod 3. And I think that really is true. I think that really is going to be true. And perhaps it's going to be, and you may have already been, you know, hinting at this, perhaps what I'm going to be doing now is going to be a lot like, it's going to be some relationship between what I'm talking about now and what you were talking about in the first part of today's discussion, which was something called Galois descent. Well, we'll see how it goes. We'll see how it goes. So on the screen that's hopefully visible to all of us is some stuff, which was pictures. This is some version of pictures that we were already drawing last time, and it has a lot to do with the number 3 because of the fact that we're interested in Z mod 3 torsors. So in fact, right, I mean, this picture, it's a sort of poset or lattice picture, and it's a picture of the Galois correspondence for subfields of a certain field. It's not quite the whole 63rd cyclotomic field, but it's like half of that. The 63rd cyclotomic field is 36 dimensions over the rationals. This is just 18 dimensions over the rationals. And it's kind of because we are taking that subgroup to give us a kind of threshold, a kind of lower bound on subgroups, or an upper bound on subfields in this contravariant Galois correspondence. So we don't get any subgroups that are smaller than that, and that means that we can draw them as these little 3x6 rectangles instead of as the full 6x6 rectangles, because the other half of the 6x6 square is just a repeat of the top half. The bottom half is just a repeat of the top half, as you can see in this example of the smallest subgroup. 55 is just kind of a repeat of the 1 in terms of the position in the little square there. So yeah, we're supposed to understand how this is a picture of the Galois correspondence for certain subfields and certain subgroups. And the fact that the number 3 is so involved here is supposed to mean that this is good for helping us understand Z mod 3 torsors over the rationals. But again, how is the number 3 involved here? Well, we've got this number 63, and first of all, it's got a factor of 9 in it, and 9 is very related to 3. So that's one of the ways that 3 is really involved here. But another way that the number 3 is involved here is that 63 is 9 times 7. And 7 is this correct? It's the first prime that we can think of that's congruent to 1 mod 3.
Mm-hmm.
I think that might be true.
So its multiplicative group has an order divisible by 3.
Yes, exactly. And that's why this is good for getting Z mod 3 torsors going somehow. Yeah, so that's what we're doing here. And so, maybe a week or 2 weeks ago, right? I guess 1 week ago was kind of me just fooling around with this Galois correspondence and doing it in a very ad hoc way. But 2 weeks ago, we actually had more of a conceptual plan planned out. And the plan that we were trying to plan out was this very Tanakian, or at least what I call Tanakian, this very Tanakian philosophy, this plan that really tried to use the Tanakian philosophy. And in other words, so what did I mean by that? And what do I mean by that? I mean that we're trying to understand these Z mod 3 torsors over the rationals to begin with. We're trying to understand them from the Tanakian viewpoint, which means we think of them as these nice functors that go from the representation category of Z mod 3 to the category of rational vector spaces. And so we're really thinking about the representations of Z mod 3 over the rationals. And again, the sort of halfway fun, halfway challenging thing is that Z mod 3 doesn't split over the rationals, so that we have just 2 irreps of Z mod 3, one of which is 1-dimensional and one of which is 2-dimensional. And the 2-dimensional one sort of wants to split into 1-dimensional irreps, but it can't do that until we get to the Eisenstein field. Right, let's remind ourselves of the comparison to the Z mod 2 case. So in the Z mod 2 case, we had this, classification of Z mod 2 torsors as just something like square-free integers or something like that. Z mod 2 torsors over the rational numbers. And it's just kind of square-free numbers. But we gave a Tanakian story about why that happens. And the story about why it happens was that a Z mod 2 torsor is basically, well, let's put it this way. We have the representation category of Z mod 2. And we can just sketch that category as a theory in the doctrine that we like, this doctrine of total 2-rigs, or whatever we call it. By the way, this might even work better if we worked over Todd's doctrine of absolute 2-rigs, or at least certain parts of it would work just as well, or, I'm sure Todd would consider a selling point that a lot of this would work over the working with the absolute 2-rigs. But I have reasons also for liking to work with the total 2-rigs. So we're thinking of the representation category theory of Z mod 2, and then later of Z mod 3. We're thinking of these as theories in our doctrine.
Mm-hmm.
And for Z mod 2, we think of it as the representation category. It turns out we can actually think of it as the theory of a line object equipped with a trivialization of its tensor square. And that provides a very simple, straightforward account of why the Z mod 2 torsors over the rationals are classified by the square-free integers, or something like that. I'm not sure I said that exactly right, but it's something like that. And it's and again, it's right. It's this kind of gauge fixing thing that you were talking about. I mean, we're trying to get these. I guess I'll try to draw something here. Our whiteboard here is so crowded, but I'll try drawing something here, and then I'll try to erase it on account of how crowded things are here.
Yeah.
So what was our idea? Our idea was that a Z mod 2 torsor looks like a line object L and then a trivialization of its tensor square. So that's like an isomorphism to the tensor unit. And we're supposed to take the isomorphism classes of these things. And we thought about that, and we saw how the isomorphism class of these things, in a somewhat elegant way, turn out to be classified by the square-free integers. Basically, because, if you have another one of these things, let's say L prime, and it has its own trivialization, and you try to figure out what so the isomer, after you gauge fix, you take advantage of the fact that all rational line objects are just the one-dimensional vector space because we're working over a field. We see that this isomorphism, this trivialization just amounts to a single quantity, a single number. So the data is given by a number to begin with, but then we have to account for the isomorphisms. And so we have like, this is right. We need an isomorphism between the objects L and L prime. So we'll call that something like, I don't know, A. And but this is between their tensor squares. So we're saying like, the number A squared. And over here, it's the 0th tensor power. So it's the number A to the 0th, which is 1.
Yeah.
And,
by the way, you're missing a little 2 next to prime.
Thank you.
Tensor square.
Okay. So this is just trying to remind us of how this syntacto-semantic philosophy of describing the representation category leads us to see in a very direct way that we're classifying the Z mod 2 torsors by the square-free integers. Okay, but now, like I say, that we've got a very crowded whiteboard here, so I'm going to try to erase a lot of that. And we're going to try to think about the Z mod 3 case. So we're looking for a similarly elegant syntactic description of this representation category of Z mod 3. And, if we were working over, if we were already up to where the group Z mod 3 splits, if we were working over the Eisenstein field, then we could, then the story would be very similar. We would just say that we had the theory of a line object equipped with a trivialization of its 3rd tensor power. But our whole goal is to get beyond that. We want to understand what happens before you get to the point where the group splits. And I'm sort of hoping that you're already anticipating that means we're doing sort of some kind of Galois descent.
Something like that.
Well, yeah, something. Let's see how it goes. But the way I'm thinking of it is I'm just trying to give a sketch of this theory. This right? There's this category. There's this 2-rig. There's this total 2-rig, which it's kind of like it's kind of like a 2 vector space that has a basis of 2 irreducible objects. But it's funny because one of them is a 1-dimensional irreducible object and one of them is a 2-dimensional irreducible object. And I guess you've been teaching me at some point that means that the 1-dimensional one has a very vanilla endomorphism algebra. They both have division algebras for their endomorphism algebras because they're both irreducible. And you probably told me there's some buzz name that I should associate with that. Is there a lemma or a theorem that?
It sure is lemma.
Just lemma. Okay. Maybe I'm used to some less fancy version. I'm sure.
The less fancy version is like Schur's lemma over an algebraically complete field.
Okay.
Just the feet, the only things that commute with everything in an irreducible group representation then is just the field itself, but
Okay.
here you get more choices.
Okay, so our one-dimensional irrep, which is the trivial irrep of Z mod 3, is just going to have that very vanilla endomorphism algebra, which is the field itself, the rational field itself. But when you think about the two-dimensional irrep, and you think about its endomorphism algebra, and what kind of commutative division algebra that gives us the Eisenstein field. So again, I have this vague feeling like that in this context, there's like no escape from the Eisenstein field. I mean, I started out with the goal of sort of understanding cubic reciprocity and understanding Z mod 3 torsors and understanding them without any reliance on the Eisenstein field. But it doesn't work like that. The problem itself forces you to think about the Eisenstein field, because the Eisenstein field shows up in the problem as the commutative division algebra that is the endomorphism algebra of the two-dimensional irrep of Z mod 3 over the rationals.
Can you remind me, like, what's a simple problem whose answer involves the concept of Z mod 3 torsors over a field? That is,
well, I mean,
reciprocity, but what exactly is the?
Well, so we're looking at abelian cubic extensions of the rationals.
Okay,
And that's almost the same thing as a Z mod 3 torsor, except that it's kind of like it differs by a factor of 2. What am I trying to say? That, you know, because Z mod 3 has an automorphism group of size 2, because it has a non-trivial involution, that, what am I trying to say? That each abelian cubic extension of the rationals actually corresponds to 2 different Z mod 3 torsors.
so that's that like,
yeah,
that like related to how it's, are you saying like its Galois group is S3? Really? Not, or the it's not, its Galois group is not just Z mod 3.
well, actually these are just because they're abelian, they're just Z mod 3.
Oh, okay.
But
Oh,
but there's some, I'm doing a bad job. I'm hoping maybe I can sweep this under the carpet for the moment and then return to that question when we're in a better position to answer it. But it is true. Z mod 3 torsor and abelian cubic extension of the rationals, those are almost synonymous. It's just like a glitch, which is a factor of 2, that each abelian cubic extension of the rationals corresponds to 2 Z mod 3 torsors, and it's because Z mod 3 has this involution or something like that. But that's a horribly sloppy way to say it. I don't know why I can't think of the right way to say it, but hopefully we'll think of the right way to say it when we're in a better position to think about that. Is that okay for now?
I guess it'll have to.
I very weaselly answer for now.
I guess it has to be, yeah. Yeah, I don't like it, but I'll live with it.
Well, yeah, no, but you really should see it, because I'm about to give an elegant definition of what a Z mod 3 torsor is.
Yeah, well, I know, but
you want to know the unelegant.
that, but then I was like forgetting, like, why do we care? And so that is, why do we care, starting from the
well, remember, right? Remember, a torsor, right? There's another viewpoint that says if you don't focus on the variability aspect of torsors, then a torsor is just like a group that has forgotten its base point.
Yeah.
So, you know, a Z mod 3 torsor is this thing that's kind of like, you know, right? That's why it's a 3-dimensional thing, you know, over the base field.
Yeah.
And
Yeah, okay. Anyway, I can live with this. I mean, I'm in.
okay, yeah, right. If right, this is, I'm not doing it the best way, obviously, but
So you're gonna, but I am also interested in what you're about to say, which is to
yes,
give me the promised clear description of Z mod 3 torsors over a field, I guess.
right, and again, there are all sorts of better ways than the way I'm about to do it. In other words, I should give you some way where I take you on a story where it takes me through the reasoning that I got here. But at the moment, I'm going to sort of jump into a bit of an answer here, and the answer goes like this. This representation category of Z mod 3, it is the theory of, I hope I can say this right. It is the theory of an Eisenstein line object equipped with a trivialization of its third tensor power, but furthermore equipped with one other very important thing, and that is an isomorphism between two things that you can do to it. So one thing that you can do to it is you can take its Eisenstein conjugate. In other words, you can apply, right, the Eisenstein conjugation, the involution, the involutory automorphism of the Eisenstein field. You can apply that to an Eisenstein line object.
Uh-huh. Get another one.
Yes. And
so this is where that Z mod 2 involution is.
Yeah.
Going on.
Yeah, absolutely. That's part of what's going on here. Yeah. And but there's an isomorphism between that and right, an isomorphism between that and the thing that you get. Right, okay, an isomorphism between, let's put it this way. There's an isomorphism between the thing that you get by applying the involution of the Eisenstein field, applying that to the concept of an Eisenstein line object. And again, you sort of have to remember that this is a formal Eisenstein line object, in the theory, because you can express the idea of an Eisenstein line object, an Eisenstein vector space, all those things. You can express that idea in the syntax of the doctrine. That's why it makes sense to talk about this stuff. So you can apply the involution, you can apply the involution symmetry of the Eisenstein field. You can apply that to the concept of an Eisenstein line object. And in that way, you get a new thing from your original Eisenstein line object.
Sorry. Oh, that's sorry. That's different than the first thing you said. Okay.
No, that's not different yet. That's not different yet.
Okay, that's the same. Okay, that's number one. So okay, yeah. So
and now I was worried that I was about to forget the second one, but I think I'll get the second one. The second one is instead we're going to apply our other involution symmetry, which is the involution symmetry of Z mod 3. Right? So where do we have that apply? Remember, we said that to begin with, we have an Eisenstein line object together with an Eisenstein line object together with a trivialization of its third tensor power.
Yeah. By the way, can I interject? When you say third tensor power, you mean like its third tensor power over the Eisenstein
exactly
numbers, which is a thing you can do even though we're working over some other.
That's right. That's right. And I always invoke Jeff Egger's name whenever I think about that, because I was so stupid that I didn't even understand it until he explained that to me. But you can see it very concretely, right? That an Eisenstein line object as a rational vector space is two-dimensional. Right. So if you just use ordinary tensor product, you're going to get, by the time you take third tensor power, you're up to something 8-dimensional.
Right. That's what I was. At first, I thought you meant that, and then when you said that it was supposed to be isomorphic to the trivial line object, and that couldn't be, so I knew you must mean tensoring over the Eisenstein numbers in some clever way, which I think I can see.
That's right. That's right. And so all of this stuff is in a certain sense what I call formal. So it's a formal Eisenstein line object and a formal trivialization of
Yep.
its formal third tensor power, et cetera, et cetera. And there's all sorts of fancy highbrow ways to think of that in terms of like categorified synthetic differential geometry and stuff like that. But I don't want to about that right now. There's very nice highbrow ways to think about it, and there's also very nice lowbrow ways to think about it. And we really want to unify those different brow levels at some point. And so we've got
Can I think
so
so like I think you could say that the one way to say it is I think there are like two ways to get a new Eisenstein line object from an Eisenstein line object, one of which is to use the involutory automorphism of the Eisenstein field to turn the Eisenstein line object into a new one.
That's right.
And the other is to take the tensor square.
That's exactly right.
Of the Eisenstein line object, tensoring it over the Eisenstein's form.
That's exactly right. That's exactly right.
Yeah.
That's exactly right. And that's very close to being the end of the story, except, well, first of all, I hope you sort of see that that's a Galois descent thing in some sense. Doesn't that sort of feel, I mean, I hope you see as well as I can see that in some sense that is a Galois descent thing that's going on here. Right? I mean, right. I mean, the thing that's playing the role of that Galois extension that you were talking about in Galois descent is this Galois extension given by the Eisenstein field as a Galois extension of the rational field. And so we're sort of trying to classify these things, which are Z mod 3 torsors. I mean, I'm not trying to see it completely fitting, but it's something, it's really similar in flavor to the story you're describing. We're trying to describe something, the classification of Z mod 3 torsors over the rationals, but we're going to this auxiliary covering or co-covering or whatever, which is given by the Eisenstein. Yeah, we're pulling back to the spectrum of the Eisenstein field or something like that. But we're pushing forward, algebraically pushing forward to the Eisenstein field. And the answer is much simpler over the Eisenstein field. But then we, but then we have to compensate for the fact that we're doing it over the wrong field. And it's kind of a weak fixed point thing or something like that, right?
Yeah, so I was saying
something like that.
Use Galois descent for all sorts of algebraic gadgets. And so I guess there's like one type of gadget here, which is like a
Z mod 3 torsor, maybe. I mean, I don't know. I wasn't prepared for your description of it. So I'm still trying to put it together. But something like this is going on.
I was going to say one of them is like an Eisenstein, Eisenstein line object is a thing.
Well, that's very closely related to the Z mod 3 torsors.
Right. But anyway,
yeah, I mean, you're hinting at a whole bunch of interesting things there. But right, I'm sort of trying to be ridiculously compressed and ridiculously fast here, which is a bad idea in so many ways. But let's proceed. Let's proceed. So, well, first of all, I said that we're almost done, and again, we're probably about as done as we were in the Galois descent case, or as about as done as I was in the Galois descent case. Because in the Galois descent case, when you talk about the weak fixed points and everything, there was that point where I was sort of almost completely following you. And then there was this bit about the coherence laws. And I said, I think I sort of know how to handle that, but I always get confused about it. And the same kind of thing is going on here, right? In other words, do we have to add any extra kind of coherence law here? I'm not quite sure. It almost seems like we might, in this Z mod 3 case, it almost seems like it might be such a simple case that we might not have to really worry about any coherence things or something like that. Whereas in the ZMod 2 case, right, I think we somehow got away without worrying about any coherence laws. And that was an even simpler case or something like that. And I'm not even sure why we got away with it, but we did get away with it. But if we start doing something like ZMod 5, then I have a feeling we might have to really, maybe we'd have to start thinking consciously about the coherence laws in the Galois descent type thing.
Yeah.
Right? I mean, what would be the analog in that case? We would have, instead of just a single involution, we would have an action of GL1 over the ZMod 5 or something. So that would be this 4-element cyclic group, and we'd have a 4-element. Oh, maybe you could still get away with that. I don't know. But I'm still have a feeling I might have to worry about coherence laws at some point. But I don't think we have to worry about them too much yet. So I'm claiming that this, even if I'm waffling a little bit about whether we need to worry about a coherence law or not, I'm claiming that this is actually a fairly elegant description of this theory. And it will allow us to get pretty specific about what these ZMod 3 torsors are and what all these, these fields that we're dealing with. Well, so these are the, cubic extensions of the Eisenstein field. So these are like ZMod 3 torsors over the Eisenstein field. So, right, by our previous reasonings, this should just correspond to taking these could just correspond to taking the cube root of some particular Eisenstein integers, each one of these 4.
Oh.
Whereas for these ones over here, these are, these are corresponding, each of these corresponds to a pair of ZMod 3 torsors over the rationals. And the way to describe them will be sort of, again, it will be this sort of Galois descent thing, and that will actually jump up to, we'll jump up from here to here, which is kind of jumping up from here to the Eisenstein thing or something like that. But then we'll compensate for that when we come back down, that's some part of the descent process or something like that. Except, again, I have no idea which way is up here, so don't think that I'm claiming that the coming back down part was the descent. It might have been the other direction that was the descent. I can't quite tell. I think by some compensation of errors, I think coming down descent really is going downwards in this picture. But I think that's some funny compensation of errors because it's really supposed to be a geometric picture. I don't know. Right? Could have something to do with the.
Yeah, you've got the Eisenstein integers above the rationals. The Eisenstein rationals above the rationals, and so.
I'm so scared I'll make a mistake about this. I shouldn't even think about it.
That's like the covering space.
Right. Okay. So
by coincidence.
So this undoing now correctly?
Yep.
Come on, undo one more. It's slow or something. Well, I'll try to talk while I'm waiting for it to undo if it can. So I'm gonna try to give you a sort of plausibility argument or a plausibility calculation here for what special kinds of Eisenstein integers we're going to be taking the cube root of here. So let's see. Well, let me give one example, and I'm not sure yet which one of these 4 it is in the diagram, but I'll say the example, and then we'll try to fit it into the diagram somewhere. Okay. So what am I trying to say? I'm going to think about the Eisenstein prime 7. Okay. No, sorry, the Eisenstein number 7, which is conspicuously not an Eisenstein prime. Even though it is an ordinary prime, it fails to be an Eisenstein prime. It factors over the Eisenstein, because it's equal to 1 mod 3. It actually factors. So how does it factor? I'm trying to remember what it is. Is it 1? Where's my undo thing here? Is it going to be 2 plus 1 to the 1/3 times? I'm not sure I've got this right, but you're good at this kind of thing. You should be able to figure it out. You should be able to check my arithmetic. That's supposed to say 1 to the power of 1/3, and this one is supposed to say 1 to the power of 2/3. So does that come anywhere close to being an equation? And if not, how can I tweak it to get it to be an equation?
What's 1 to the 1/3 plus 1 to the 2/3?
It's well, because those are,
yeah, I mean,
it's
I'm just
-1 because of the, all 3 cube roots of unity balance out to be the origin. So that means any 2 of them are the negative of the other one.
Yeah. This doesn't look like it's working.
Should I make it 1 plus 2 times the? Let's see.
You're getting 2 times 2 is 4.
Yeah.
Plus 1 to the 1/3 plus 1 to the 2/3, which is -1. Plus 1 to the 1/3 times 1 to the 2/3, which is 1. Right.
Okay. So what do we need to do to get this to work? I did this just the other day, and should I make it 1 plus 2 or something like that? Let's see.
Oh, maybe I did something. Sorry. No, I think I did something really stupid there. But it still is not going to work.
Okay.
So actually, what you're getting is 2 times 2 plus 2 times 1 to the 1/3 plus 2 times 1 to the 2/3. So far that's 0.
Yeah. I mean, can you figure out how to factor 7 over the Eisenstein integers? I thought it was something.
I think your number 2 there is not big enough, basically, is what I think. I think you need something a little bit bigger than that. I'm thinking.
What if I did it the other way around? What if it was 1 plus 2 times 1 to the 1/3? That wouldn't help.
Good.
And right? I mean, they're both supposed to be Eisenstein conjugates of each other. So,
yep.
Any chance this one will work out?
Let me see. So that's 1 plus 4.
How are you getting plus 4?
Minus.
Oh, okay, plus
2.
4. I guess that's right.
1 plus 4 minus 2.
Really? Then okay. Then you said the 2 is too small. Let's try the 3. Let's try the 3.
So then we're getting 9.
Yeah.
Minus 3 plus 1. That sounds great. Yeah. I think 3 does the job instead of the 2 there.
What should it be? With the 3. Does it matter whether it's the 3 plus 1 or the?
No, both of them should be. Both of those 2 should be 3s. I mean, they got to be conjugate anyway. So on your top line there, just change.
I should use the top line. You're saying cross out my bottom line.
Just think about it with the 3 there instead of a 2, and I think you'll. Unless I'm doing something dumb.
Okay, so it sounds like you're saying 3 and 3. This might be true.
Let's see. I think you should multiply it out and see. Yeah.
All right, so I get 9 and one is 10. And then I get a -3.
Yep.
Okay, so I think that's true. I think that's
Okay,
true.
good.
Okay. So I'm going to describe a simple-minded, calculational prescription. But then you're supposed to think about it and see that, oh, this is actually doing what we said from the fancy Tanakian viewpoint. So what I'm saying is this: take this number 7, factorize it as we just did, and now take one of those factors and put it to the power of 1, and take the other factor and put it to the power of 2, and recombine them.
Why are we supposed to do that?
Think about it, right? Think about what our theory said, right? Our theory said that this is the theory of an Eisenstein line object together with a trivialization of its third tensor power, and together with an isomorphism, between those two things. So it's right. It's not just an isomorphism of Eisenstein line objects, it's an isomorphism of Eisenstein line objects equipped with trivializations of the third tensor power, or something like that. And this extra thing is an isomorphism between, the thing that you get from applying the Eisenstein conjugation involution with the Z mod 3 involution. So.
And so you're saying that Z mod 3 involution corresponds somehow or other to squaring one of these factors, because
yes,
squaring in Z mod
3, yes, I hope I'm saying that
Z mod 3 corresponds to negation. Yep.
Yes, and applying the involution, we mean that the one that has the 2 exponent will get the 1 exponent, and vice versa. Whereas applying the Eisenstein conjugation just switches these two prime factors, these two Eisenstein prime factors of 7. And right now, so there's all sorts of things to clean up here. But that's what I'm trying to say. I'm trying to say that this simple-minded calculation is an embodiment of that fancy Tanakian viewpoint about what a Z mod 3 torsor is.
So what are you supposed to get when you square one of those factors and then multiply it with the other one?
I mean, you just get an Eisenstein integer of some kind. And it's...
but then what's it supposed to equal to make you feel like you're on the right track?
That depends on what you mean. What do you mean by what is it supposed to be equal to in order to make you feel like you're on the right track? What do you mean by that?
You were saying like, oh,
yes,
you're supposed to saying like, oh, there's like some little calculation you can do with these numbers here.
Yes.
But you get some answer that like matches with the highbrow philosophy.
Yes. So we're saying that we have this
what are you supposed
L, which is an Eisenstein line object now, and we have its third tensor power, and we have a trivialization of that. So again, this is all, this should all have little E subscripts or something on them because they're all formally Eisenstein things. And right, and now we're supposed to have a quantity, a formal Eisenstein quantity. But in this case, a formal Eisenstein quantity over the rational numbers, that's just a genuine Eisenstein quantity. So we're going to have an Eisenstein quantity right here. And it's going to be this one that's like, 3 plus 1 to the 1/3 times 3 plus 1 to the 2/3, but that second whole thing is squared or something like that. So that's giving us, right, that's giving us this isomorphism That's giving us this trivialization. But then we're supposed to have these two different involutions act on this thing. And one of them is going to act by switching the factors. The other one's going to act by switching the exponents. You know, the fact that this has a 1 exponent and this has a 2 exponent.
Oh, okay. Well, that's obviously worked. Yeah, okay. Yeah, okay.
I mean, there's things to check there, but that's, but yeah, right. It is, yeah, right. It is like what I think you just said, that, yeah, you just kind of see it. I mean, you know, you do get this matchup between the highbrow way of thinking and the lowbrow way of thinking. And now, can I actually remember which one of this one with the 7, which one is it of these? I'll just try to take a guess, right? Let's just try to take an intelligent guess, because I always get this kind of thing screwed up. But where would it be in the Galois correspondence here? So C. Oh, okay. So right. Okay. Now there's another big philosophical, semi-philosophical point coming in here, and that is we're starting out with this philosophical Tanakian viewpoint about the classification of torsors here. In this case, the classification of Z mod 3 torsors over the rationals, but we're anticipating all sorts of generalization. But we have this, you know, philosophical Tanakian approach about classification of Z mod 3 torsors over the rationals, right? And right, and it will generalize to, right? It will generalize to classification of torsors of any finite abelian group over any number field, and it will generalize in, you know, pretty straightforward way. Again, I'm sort of saying that with great confidence that maybe I shouldn't have, but no, but it's really true. And that's sort of, as I say, a sort of philosophical Tanakian thing. But then we get our hands dirty and gritty and everything, and we, you know, do the gauge fixing, and we see that it ends up being this cube root of an Eisensteinian number. And we do this kind of gritty calculation that I was just trying to describe, and we get, you know, nice patterns in the gritty calculation that reflect the nice patterns in the, you know, beautiful theoretical calculation. And the upshot of that is that when we stare at the gritty data that we're classifying these things by, we notice that the data that we're classifying these things by, and again, I'm being slightly sloppy here about the distinction between the torsors and the fields, the torsors and the extension fields. They're almost the same thing, but I'm just trying to not worry about that for a moment. But the data that is classifying these things looks suspiciously like a splitting pattern, a congruent splitting pattern, a congruence pattern. The congruence patterns that tell you when something splits over something, and that is, you know, the subject matter of the reciprocity theorems of all these, you know, abelian reciprocity theorems like cubic reciprocity and Artin reciprocity and something like that. So that's a key point that's going on here. We're starting out with this Tanakian viewpoint. It leads us to this calculational viewpoint, and the calculational viewpoint tells us that we're classifying things in terms of data that looks suspiciously like the classical kind of congruence splitting pattern that occurs in the reciprocity theorems. And that's supposed to be a big hint that we're on the right track here. And then, of course, then you're also supposed to start, I shouldn't even say this right now, but let me say it anyway, that you're supposed to then start wondering about, well, what if our group wasn't abelian? What if we were trying, you know, to classify these torsors of some non-abelian group over these number fields? And, you know, that would make you start dreaming about inventing some kind of non-abelian reciprocity laws. And that's kind of one of the philosophical starting points of the kind of problem that led to the Langlands program. But of course, I don't know to what extent just thinking about the problem actually helps you invent the program. You may need more than just the desire to solve the problem in order to develop the Langlands program. And then people also argue about, to what extent does the Langlands program actually fulfill the ancient dream of non-abelian reciprocity laws? And I don't know much about that yet either. But like I say, that's stuff that I shouldn't have said because it's jumping too far ahead and talking about things that I don't really know about. But okay, now let's try to remember back where we were before I took that little detour into the idea of non-abelian reciprocity laws. So I did all sorts of checks to see that this is actually working out, and basically what and it was really fun. It was like I was doing this calculations with like Mathematica and plus all sorts of calculations on paper, and right, it was one of these situations where I had this very nice theoretical prediction. But in order to test the very nice theoretical prediction, I had to get my hands really dirty with writing computer programs and stuff like that. And when I say testing it, I mean, testing it in my way. Other people would like prove theorems to prove that the things are true. But I just, do a lot of experimental calculations to see if they seem to be true, see if the predictions come true. And basically, I think I was indicating that, I feel like I'm really making progress because this project to check the theoretical predictions against the experimental calculations, it really worked beautifully, but it worked even more beautifully because at first it didn't seem to work beautifully. It gave me so much resistance at first, which made it so much more fun. And so it's sort of like seven at one blow. I'm trying to make this sound like a dramatic struggle that I went through because it was really fun. It was really fun. But I mean, maybe in the end, it's all things that should have been completely obvious. But it's really it's really working out nicely. And so I mean, I'm almost now right. We were so late today, and I took so long. So, but I am getting really close to a place where we could, successfully declare victory and call it quits for today. But before we do that, let's just try to think about. Are we at a punchline yet? Do you follow? Is the story as I'm telling it making any sense, or am I leaving something really crucial out here? In fact, having done this for Z mod 3 torsors. Well, for one thing, it'd be nice to have a fresh sheet of paper here, fresh sheet of whiteboard here. What do? Can you give me a new?
I think I have to do it for some reason.
Okay.
Here we go.
So we can actually learn some new stuff. We can actually learn some new stuff even about the quadratic case that I thought I sort of already understood pretty well. But from this new viewpoint, even this case is making much better conceptual sense. So like what I mean is that we have, right, we often look at this 20th cyclotomic field that has like multiplicity of 2 in 20 is 2, and the multiplicity of 5 in 20 is 1, and then the Chinese remainder data looks like what? Something like 1, 11, That's it works. It's like 1 and 3 and 1, 2, 4, 3, and so what is this like? This is like, no, not 7. This is like 17, maybe? Is that right? And this is like 9 and 19. Am I doing this anywhere close to correct?
Looks okay.
And then we have, this Galois correspondence.
Mm-hmm.
And how quickly can I draw it? And I mean, there's something very interesting about this little Galois correspondence that either I never noticed it at all, or I like noticed it one time a couple of years ago and then like totally forgot about it because I didn't have the proper context to put it in. But I didn't realize that there's some nice, again, maybe this should have been obvious, there's some nice quartic reciprocity going on here, right? I mean, we were talking about, maybe I didn't use the words cubic reciprocity that much, or at least didn't explain that too much. But when we were doing all that stuff with the Eisenstein field, we were doing a lot of cubic reciprocity stuff classically.
Mm-hmm.
Sort of trying to give a Tanakian viewpoint on classical cubic reciprocity stuff. But, maybe even more famous is the biquadratic or quartic reciprocity, which is related to the Gaussian field in the same way that cubic reciprocity is related to the I'm drawing this really badly, but looks something like that.
Mm-hmm.
So let's see. So what does it look here? It's like okay. So where's the so the Gaussian field is right over here, I think. Is that right? And the 20th cyclotomic field is up there, and there's all sorts of other things. This is like here. Am I doing this right? This is like that. No, that can't be right. It's supposed to be just 2 things there, right? Let's see. Maybe it's like there.
That would work.
And this is the sort of zigzaggy one, which is interesting because it's zigzaggy. And this is this thing like this.
Mm-hmm.
So the sort of really retrospectively obvious thing, which I hadn't thought about too much, is the fact that, going up from here to here is a quartic extension. So it looks like exactly the kind of thing that should, am I saying this right? That should be taking, if you think about it, that should be like taking a 4th root of some Gaussian quantity to get up to here. But right, we already have an independent description of what this is. It's generated by the primitive 20th root of unity.
Mm-hmm. So that other one's the 5th root of unity, some 5th root of unity.
This one over here?
Down below. Yeah.
This is the 4th root of unity.
Oh, whoops.
This is where this thing is generated by the primitive 5th root of unity. Is that right? Wait a minute. Am I saying this right? Is this making sense? Yeah.
I thought that because the 4th root of a 5th root of unity is a 20th root of unity, that you'd be doing a quartic extension to go up from.
Right. I can see why you were saying that, and that's part of that's part of the confusion I went through when I was trying to figure this out. But although right now I'm really confused. How can this one be generated by, this is supposed to be the fifth cyclotomic field over here. So it's generated by 1 to the 1/5, right?
Yeah.
But how can that give us, how can just a quadratic extension of that give us the 20th primitive one? Am I screwing up something there? Like where are the 10th ones? Right. Maybe I'm getting confused by the fact that, right, it probably does all fit together, but I'm just getting myself confused that the fifth one is actually the same as the 10th one or something like that. Right, because right, in the field generated by the fifth roots of unity, it's actually got the 10th roots of unity because it's got -1 in it. So
Oh, okay. Yeah.
there's just all sorts of silly
Yeah, if I take a
traps
regular pentagon and it's negative, I get regular decagon.
Yeah. So somehow try to give me a little bit of leeway to hang myself or to not hang myself or something like that. Well, but let's see how it goes. So I can see how you're saying that, right? I mean, it seems like, right? You could think about the fourth root of 1 to the 1/20th, which would be 1 to the 1/5, but somehow that's in the wrong place or something.
I mean, the fourth power, right? Then, but yeah, yeah.
Fourth power. Okay, yes. Fourth power, yes. Right. Or the fourth root of this would be this, but somehow that's not. I'll have to think about that. There's all sorts of things here that confuse me here, but there's going to be something here that does make good sense that I hadn't noticed before. And that is what? That see, not only should we get this thing at the top by adjoining a fourth root to the Gaussian field, but from the diagram, it's also supposed to be a completely abelian extension, right? So, right, normally if we take a quadratic, normally if we adjoin a fourth root to the Gaussian field, we should end up getting something that's a non-abelian extension of the rationals, and it will sort of have this dihedral symmetry or something like that. But here, somehow, instead of getting something dihedral, we're getting this, instead of this semi-direct product between Z mod 2 and Z mod 4, we're getting this direct product of Z mod 2 and Z mod 4. That's these very unusual cases. Well, okay, so doing a lot of very sloppy things here, but let me try to say what I think is going on here. So let's take 5 and see how it splits over the Gaussian integers. And this is supposed to be we're trying to do the analogous thing we did with 7 over the Eisenstein field. So 5 should be equal to what? Something like, I don't know, 2 plus I times 2 minus I or something like that.
Yep.
That seem correct?
Yeah, this time it's right.
Okay. So we're trying to do the analogous thing we did in the Eisenstein. So we're going to take the two Gaussian factors. And again, they're just conjugates of each other. They're just Gaussian conjugates of each other. But now we recombine them, but with different exponents. And the different exponents correspond to these different elements, 1 and 3. Now the elements of the field are 1 and 3. So it's those exponents. So we're going to take like this one to the power of 1 and this one to the power of 3 or something like that. And that's going to give us a Gaussian integer to take the fourth root of. And amazingly enough, that's going to give us the same thing as the 20th cyclotomic field. So when you work this out, right, there's a whole bunch of annoying ambiguity here because you could I could have put the 3 on the left and the 1 on the right, or I could have used, 1 plus 2i and 1 minus 2i or something like that. But let's try to, not worry about that. So I think this number or some close cousin of it ends up being something like 15 minus 20i. And so I'm saying that this field that's generated by the 1 to the 1/20th, we should also be able to think of it as generated by the 4th power of 15 minus 20i. And that's one of these special quartic extensions of the Gaussian field.
Now you're saying power when you mean root. Yeah, 4th root.
Did I?
You did, yeah.
Okay. So this is like, right? I mean, this is right. This is like, right? You can see this is divisible by 5, right? Am I saying that right? It's like, this is equal to the 4th root of 5 times 3 minus 4i or something like that. Right? There's a whole bunch of arithmetic games you can play here. You can see that, right? We're recombining these prime factors in this funny way. So we still have a factor of 5 in there, right? But it's just that we have this, in addition to that, we have the square of 2 minus I in there. And somehow that's going to give us the 3 minus 4i or 4 minus 3i or something like that. And see, and these quartic extensions, right? They always go through, right? You can think of them as first doing a quadratic extension and another quadratic extension. I guess that's why Gauss or somebody called them biquadratic extensions or something like that. So, and this one is going through here. So we actually have this biquadratic, we have this quadratic extension and then this quadratic extension. So am I saying this right? Yeah. So I think the way this is going to work, you have to remember that this one here, we're supposed to know from past experience that this is generated by the square root of -1 and the square root of 5. And that is fitting what we're doing here, because we're getting this thing that is, we're taking the 4th root of something that's 5 times. So, I mean, this one here should be taking the square root of 5 times 3 minus 4i. That's what this one should be here.
Sorry, which one? By the way, I can't see a pointer when you say.
You can't see the pointer.
No.
Oh, okay.
I think that's the sad thing about this setup. Yeah.
Okay.
Yeah.
Well, okay. But I was talking about this one here, the intermediate one of the biquadratic quadratic extension, the intermediate quadratic extension of the biquadratic extension. And that, right, that should be the square root, right? Because it's the intermediate quadratic of the biquadratic. So it should be the square root of this thing, 5 times 3 minus 4i. But that should be equivalent to taking the square root of 5, right? Because of the fact that, I'm hoping I'm doing this right. Yes, because 3 minus 4i, that is a square. So, right, that's the idea that we had for for quadratic extensions, that, they're gotten by taking square roots, but taking the square root of a square doesn't matter. So, right. So it's fitting together. This crazy calculation is fitting together in this very sloppy way. And so what I'm trying to, part of what I'm trying to say here is that, by very brute force calculations, I was already able to figure out quantities that generated all these various fields. And then when I came up with these, more theoretical predictions, I was able to check the theoretical predictions against the brute force calculations. But some of the brute force calculations were giving really what seemed to me strange answers. They were giving me things sort of like this, or, that other thing I described in the Eisenstein case, where we had something that was like, well, Secretly, it was really just taking the Eisenstein prime factorization of 7 and then recombining the factors, but with one of them having a different exponent from the other. And so those numbers were looking just totally bizarre to me. And I was thinking, no way in the world I'm ever going to find a pattern that explains this. But the theoretical pattern in terms of the Tanakian viewpoint explained it perfectly and beautifully. And that's kind of what I meant by the 7 at one blow viewpoint. I felt like, oh, I'm never going to tame this ridiculous patternless pattern. But then the Tanakian viewpoint really did make it make sense. And again, I'm being incredibly sloppy in describing these, but I hope you're getting some sense of what's going on here. And maybe believing me that this is going to take care of the whole thing. This is going to take care of all of art and reciprocity.
Well, I don't know about believing the last part there, but I'd love to believe it. I feel like we haven't been doing much lately about like why art and reciprocity works. And a lot of
but now I'm trying to give that. I mean, I'm not giving the full story here. Like I say, my story is that the theoretical viewpoint tells us that these torsors are classified by things that suspiciously look like the splitting patterns, the congruent splitting patterns that show up in reciprocity laws, like the art and reciprocity law. Now, just because we're classifying things by things that look suspiciously like what they're supposed to be classified, that doesn't mean we have the correct correspondence, right? I mean, there's still that, right? So what we're saying is that we have a sort of prediction, we have a sensible guess at the correspondence between the torsors or the extension fields, the torsors and or the extension fields. There's a sensible correspondence between those and the splitting and the splitting patterns, the congruent splitting patterns. But we haven't checked yet that that is actually the right correspondence. In other words, we have to prove that the predicted splitting pattern that we're getting really is the splitting pattern for that is really the splitting pattern for the field that we're getting, that we're predicting it's supposed to be corresponding to. So that's where the work of actually proving the reciprocity law should come in. And that should be fun. And it sounds like it should have to do with more Tanakian stuff, but Tanakian stuff below the rational threshold, right? We vaguely talked about how over the rational field, there's kind of things that automatically happen, right? You have you can divide by everything. Whereas we were kind of playing around how like even Z mod 2 doesn't completely split over the integers. There's different forms of the group Z mod 2 over the integers. And so the splitting patterns, the congruent splitting patterns, those have to do with points over finite fields and things like that. So that's getting away from characteristic 0. So you're kind of going below the rational threshold. So there should still be some very fun Tanakian way of thinking about it. But I have the feeling that I interrupted something that you were going to say. You were going to give some viewpoint or thing here.
No, I was just saying I want to understand art and reciprocity. So.
Yes. I really want to understand it, but I'm claiming we're really close to understanding it. Like I say, we're classifying things by what they're supposed to be classified. We just haven't proved that the exact correspondence that we're getting is the correct correspondence, but it's got to be because because we're classifying them by the right things. So the correspondence, in this case, the correspondence sort of has to be the correct thing. But we do have to do the work of proving that. So there's probably lots of things I'm forgetting to say, but so you couldn't really see when I was gesturing with my cursor. All right, we'll have to work on that. Anything else we should do before we quit here? And does it, again, I mean, I know there are all sorts of inadequacies in the way I'm explaining things, but are you at least getting the general sense of what I'm trying to say here?
Yeah, I just want to, yeah, I just would like to see it all again.
Sure,
Done
sure,
a little bit better,
sure.
partially by
And I really am. Go ahead.
it would, even if you did the exact same thing again, I would understand it better, but also I think there's probably, it could be done more clearly, because you're sort of
Sure, and
rushing.
in a more relaxed way, and I really hoping we really can take advantage of this whiteboard setup where we really can both write on the same whiteboard at the same time. I'm really hoping that's going to help. So yeah, right. I mean, again, I have a feeling I was very unrelaxed today, in part because I got totally, the time got screwed up. But
Well, I think the main problem is you spent a long
yeah,
time while our audience was
yes,
paused drawing this
yes,
enormous chart here.
that's right. That's right.
And so one bad thing about these Zoom, I don't know, maybe it is possible. I don't know how to like take an old Zoom whiteboard and make
Yes.
it be today's Zoom whiteboard. I can view anything on my computer screen, so I could view this later, but I can't draw on it later. I don't know how to anyway.
But we think it's going to get saved.
It will get saved when I'm, yeah, so I can email you all this stuff, right? Just as like a test of the system. Yeah.
Okay. So thanks a lot. And is there anything else we should do before we quit, or we're pretty much done here?
I think I better quit.
Yeah. I'm sorry for taking so long. Go ahead. Yeah.
I like this stuff. I just want to keep digging into it to understand it better. I guess for me, in a way, the high point was the semi-concrete description of a Z-mod 3 torsor, which is something I've been worrying about for a while.
But here's another question. How well did you buy my theory that, your part of the talk and my part of the talk really did connect, that you can see that what we were doing there really was something like a form of Galois descent or something like that?
I believe it's true. Yeah, I believe it's true, but that's quite different than me being able to give like a talk where I explain how it's
sure. But I can't tell whether you're only understanding it as well as I understand it, or whether you're not even understanding it that well.
I thought I was understanding it better.
Could be.
But I understand. I think maybe you understand the Galois descent perfectly well, but what I feel like I understand that part. And so like anytime you say like, here's a structure over some algebraic structure over the rationals, and then here's the same kind of structure over the Eisenstein integers. And then I'd like to understand it over the rationals, but it's sort of easier to understand it over the Eisenstein. I meant the Eisenstein rationals.
Yes.
Yes. And you like first classify it over the Eisenstein rationals, and then you like need some extra oomph to classify it over the rationals. That part I quite believe is Galois.
Yes.
And so that part I get.
That's right.
Yeah. But there's still a lot to be worked out here. There's something self-referential about this particular example of Galois descent, because the structure you're studying for the Eisenstein integers are these Z-mod 3 torsors, which seems so much like the Eisenstein integers already.
Yeah, there is that, right. And that's not even the only way that it feels peculiarly self-referential. There's also something.
Yeah, I mean, you saw it in this other way that you said, like, okay, I don't want to work over the Eisenstein numbers. I'm going to work over the rationals, and then the Eisenstein integers pop in the door and say, we're still here. Yeah. So,
but also the fact that the things we're trying to classify, which are these torsors, those seem to be something that's very fundamental to Galois theory. So
Oh, yeah, right. So it could be that this is like,
the baby base case of everything or something. I don't know
yeah, well, I was gonna say it's like
what.
just somehow like a tricky case of Galois descent because you're trying to imply itself or something or other like that.
Right.
Not
Or it might,
itself, but
or it might
something
be,
similar to itself.
yeah, or it might be easier because of that or something.
Yeah, maybe ultimately easier, but it's confusing, right?
Okay.
Anyway, it's fun though,
Okay.
which counts for a lot. So.
Okay. All right. So I guess bye for now, I guess.
Yep, I guess I gotta quit. Yep.
Okay. Bye.
Okay, see.
Okay.